vicsek,
Vicsek.
vicsek, oh, model, yes. Thank you.
Well, thank you. Thank you very much for being here after lunch. And I want to thank the organizer for the opportunity of being here in the very nice workshop and to talk about what we are working on in the physics, which is this Physics Institute of Liquids and Biological Systems at the National University of La Plata in Argentina, close to Buenos Aires. And well, I decided to talk about the work we did with Ernesto Loscar, Andrés de Virgilis, and Tomás Grigera. We all worked together in the institute, in the ICTP. And well, why we are interested on this kind of models, this kind of active matter systems, and well, this is because Tomás Grigera, he works with some collaborators in Italy in the study of birds, and also in the study of this kind of mosquitoes, midges actually, and I was working with some biologists in La Plata in the study of this kind of tadpoles, and all of these systems, they are characterized by particles that move, birds, in this case, in an ordered flock. These mosquitoes that are in a critical region that I will explain later, and this kind of horrible animals that it calls tadpoles. What I am actually studying of this kind of system is that these kind of tadpoles are sensitive to the presence of pesticides in water. So these kind of pesticides affect their swimming activity. So, but well, they are just a few in the experiments, and they are, in general, they swim in a very random way. So all of these kind of examples that we are currently studying have something in common, is that they are self-propelled particles from the point of view of physics and not from the point of view of biology, but we are physicists. So what I am going to talk about is not this work specifically, but something more theoretical or more like us, more physics, more physicists. So why you are interested in active matter or in active system? Well, several talks previously talk about that, but what we are focus our attention is in system that in some way transform the free energy in movement, the movement of particles, and each particle has his own speed, his own velocity. We don't care where it comes. Just we care about that these particles moves, and what we care more about that, or more, and when we focus our attention is that all these systems are in an out of equilibrium system, model, or nature, and because we are statistical physicists, we are interested in the description and in the develop of some tools that allow us to understand the out of equilibrium nature or the out of equilibrium system. So that's what I am going to talk about in this talk. So we started with a very, very simple, the simplest model that it was introduced by Vicsek several years ago, I think in 1995. More of you, I don't know, we are children or not born yet. But what this kind of models that have several ways to implement this particular model, but are all of these kind of model are try to explain in a very simple way and with very simple rules the collective motion of particles. That's what we are interested in. But the idea, where is the pointer? I can see it. Well, what we propose is that, or what vicsek proposed, was that there is a particle, the I particle, that has its own velocity and try to align its direction of motion according to the direction of motion of its nearest neighbor, defining that all the particles that are in a circle, or in our case, in a sphere, because we work in a three-dimensional system. So all these, the I particle, try to align its direction of motion according to the direction of motion of its neighbor, but this alignment is not perfect because there is some kind of error that it is considered in this term. Well, the laser doesn't work. Yeah, this is the black arrow corresponds to the average velocity of all particles within this circle, but this alignment, as I said, is not perfect, so particles in some way have some error in the alignment, and this is what we put in this term that it calls noise, or external noise, like a temperature. When the noise is 0, the alignment is perfect, and with the noise is non-zero, this alignment has an error. So what we have is that at each time step, we can update positions and velocities of particles following very simple rules. And this way to introduce the noise, it's called vector noise, and it was actually different for the initial proposal of vicsek, but for us, and for what we are going to try, or what we try to study, it's better this kind of noise introducing as a vector, or proportional to a vector, than the initial that it calls angular noise. So we just focus on this, and well, the positions are just updated as usually in a very classical way. So what happened with these very simple rules is that we have the possibility, or we have a phase transition that goes from a system that is completely disordered, particles move in a random direction, to a phase where particles move in an ordered way, like a flock. And in between, and in this case of vector noise, and in between we have a coexistence phase that is composed by bands, so particles that move in a very dense band, separated by something like a liquid, disordered liquid or a gas. So this phase transition is of the first order phase transition. We know that because it was a very studied model, and the order parameter that describe this transition is just the polarization, or the average value of the velocity of all the system, of the particles. And the only control parameters of this model and of these phase transitions are the external noise, the speed, that it is constant for every particle, and the density of particles that we are going to fix. No? So we only have this parameter as a control parameter of the system. So what I want actually to talk about is the use of a technique that is also a very old technique. It's a computational method to study phase transition that it was introduced in like 36 years ago. That is very useful to study phase transitions and to characterize phase transitions in principle in equilibrium system, But we are trying to apply this technique to an active system. That's the main idea of the talk and of the work. So what is the main idea of this technique, computational technique, is just to study the early stage of some observables, some relevant observables in the system, such as the order parameter and its moments, for example, the susceptibility or the second order Binden cumulant, or whatever. And the idea is that if we study this early stage, we can extract from the behavior of these kind of observables as a function of the time. We can extract all the information related to the phase transition. For example, the critical exponents, obviously the critical points, and in the case, if we have a first order phase transition, as in our case, the spinodal points, so the metastability limits. So, what's the main idea of this very simple of this technique is that we have to start the system from two special initial configuration that corresponds to trivial fixed points. For example, this is for the Ising model, no? This is not our plot, just for the Ising model, because it works perfectly in the Ising model as everything. But we have to start the system in a completely disordered state. In this case, it corresponds to the paramagnetic phase, and in the completely ordered initial state. It means in the ferromagnetic state. So what happened when we start the system in this kind of special initial condition, and we are close to a phase transition, is that for example, in this case, the magnetization, but the order parameter start to increase monotonically. It's very hard to say in English and in Spanish and in every language, that word. But has an increase or a decrease in a monotonic way. So we can measure the power law behavior and the exponents of this growing or decreasing process, and extract from them all the characteristic or all the characterization of the phase transition. So, just one more thing about this is that, and why we are interested in this particular technique is that because we study the system in these special cases, and just because we are interested in the first early time stages or evolution, we don't have the problems, the classical problems that we have when we study phase transitions, such as, for example, the critical slowing down or the finite size effect. So the main idea of this technique is that we are going to have this power law behavior, and the best power law behavior, it will occur only at the critical point. So that's why that allows us to identify the critical point of the phase transition, and by extracting all the exponents of this power law behavior, we can relate these exponents with the classical exponents of a critical phase transition in the case of the continuous phase transition. As I just put here, which are beta, gamma, nu, and zeta, but well, are all the critical exponents that we have in a classical phase transition of second order or continuous phase transition. So if we have this, we can then, we know where is the critical point, and we can measure in some way all the critical exponents of this phase transition. And what happens if we have a first order phase transition is that this power law behavior, it actually happened because we are in a finite size system, but it happens at different values of the control parameter. In our case, the noise. In the case of the icing model, if we have some kind of magnetic system with the first order phase transition, it will occur at different temperatures. But the idea is that because we have this power law behavior at different values of the order parameter, we know that the transition present in the system is of the first order, and the difference between these two values give us the strength of the transition. So, because they are just the limits of metastability of the coexistence limit in the phase transition. So, well, this works very well for I think I put here, no. Well, here is a report. It's a review we wrote several years ago about that for a different universe of systems. But well, we want to know if this technique is possible to apply at the vicsek model or at an active model. And well, obviously the answer is yes, because that's why I am talking about that. But what we started this analysis just not with the vicsek model, but with what we call a static vicsek model. That means particles that have the interactions between their neighbors as a vicsek, trying to align its velocity, but it doesn't move. So it's like something like the limit of zero speed of the vicsek model. And we studied this. I insist this is a three-dimensional problem, but I just make this kind of two-dimensional plots because it's easier. And we study the system in two geometries. One is like a lattice, and the other is just particles put in a random way that we call Poisson graph, random graph. And well, I just want to say that in this case, where we are a lattice, we know exactly the number of near neighbors that each particle has, 6 in the case of 3 dimensions. And in this case, if we fix the density equal to 1, the average number of near neighbors is close to 4. So it is lower. And well, this is what we have. A power law. Here, a power law. When we started with a disorder initial condition, a power law when we start with a order initial condition, also a power law in the second order Binder cumulant for the Poisson graph, all randomly placed, and in the lattice case also we see the same behavior, but with the exponents quite different between them, and the values of the eta values are different in both cases, but are equal for their order and their disorder case. So we know what we can say is that the phase transition is a continuous phase transition, but something happened between these two cases. In case, just to be sure about what we are doing, we implemented the classical finite size study, by, for example, studying the behavior of the fourth order cumulant, binder cumulant. We know that all these curves have a crossover at the critical point. This is very classical study. And well, it seems that everything is okay, maybe except this difference that I can summarize here. And what we see is that when we have this kind of interaction, remember that this is a vicsek interaction, we have the same exponents like as in the Heisenberg model. It is, everybody says that the limits of zero speed of the vicsek model is the Heisenberg model. Well, actually, what we, at least for this density, what we can say is that depends on the number of nearest neighbor, the coordination number that we have in the problem, in the system. So when we are in the lattice, well, obviously the interactions give us the same exponents as in the Heisenberg, but when we are in a random graph, it not happen the same. But well, it could be. And what happened, and this is the most tricky thing, because everything works, but not as we expect. What happened when particles start to move? So what happened in the vicsek model, and it is just, I don't want to talk about all the details of that, but everything or nothing is a bed of roses, no, nothing is perfect. And what happened, it was like when we tried to start the system in the ordered state, the completely ordered state, well, which is the correct ordered state in this kind of models. So, well, we know that flux are, the flux configuration corresponds to an ordered phase, but also this kind of bands that have order are the initial state where we are having order. So this is that all the thing take us a lot of time just to try to build the proper initial condition in an ordered state. And well, just testing, prove, error, and testing a lot of different ways, what we find is that we need to properly prepare the system by just, for example, I put here PU and SU, it means parallel update and sequential update. I don't want to talk about much, it's more details. If you want, we can talk about later, but this idea is that we can update all the lattice at the same time. This is the parallel update, and the sequential update is that we choose one particle, and we update the particle, and then we choose another particle, and then update that other particle, all the n particles of the system, but in a different way. Obviously, in an equilibrium system, or in an equilibrium problem model, both kind of updates goes to the same state, but it doesn't happen the same when we are in this kind of active matter and in a finite system. Remember that we are studying that, all this in a very small systems, like 27,000 particles, that means L of order of 30 sizes, and in a very small Monte Carlo steps time. So the idea is that, well, we can study and we can extract all the information about the phase transition just by studying small system in a very short time, but well, we have to pay a cost, obviously, as everything in life, and in this case is the preparation, the proper preparation of the initial configurations. But, well, after that, we finally can extract, or we can find this power law behavior, the monotonic increase, the monotonic decrease, and for different values of the control parameter, which is give us the information that the transition is of the first order that we already know, but we have to test that. And well, the main thing here is that, as I said, see the time scale is only 1,000 Monte Carlo step time, so it's very short simulations. And well, this is a good business for us, at least. And well, obviously we test everything, like performing the classical finite size study, studying the fourth order cumulant, and all it works, seems to work okay. The phase transition goes to this very minima, sharp minima, when the lattice size grows. Also it happened that the order parameters goes sharper at the critical points, as we have in the first order phase transition, then everything works. And the other thing we have also is that we can extract the metastability limits. So we know that in all this region, we have a first, the coexistence phase, it's kind of bands with gas or some sort of gas around. And well, we have also we can extract the thermodynamic limit of the critical point, and well, everything works great. So, okay. For finishes, finishing, I just put some conclusions, the beautiful conclusions and not the hard work, just to let you know that it seems that this kind of technique, this very old technique, you know, is 1989. It seems to work to this kind of models, and well, we are actually, we are currently studying another active matter models, more complex. Well, in the next workshop, I will show you the result. But well, I want to show you why we are studying a square lattice, and this is La Plata city. It's a perfect square city designed by Dardo Rocha, architect. Well, this is the cathedral, this train station, the Natural Science Museum, I'm sorry, but this is the Diego Armando Maradona Stadium, I have to say it, at the University of La Plata, at least the main building of the university. And well, exactly in this point, there is the IFLICIB, our institute. This is the front door. This is the indoor asado. So I think that maybe this is one good reason to visit us when you will be at Argentina. And this is all the staff of our institute. And well, thank you for your attention.
Thank you, Leticia. Very nice talk.
I'm sorry for my English. I have to say that in Spanish, this talk, it will be the best. But well, it is what it is. Yeah.
Okay, thank you for your presentation. It was very complete.